Welcome to today's problem walkthrough. We'll be tackling a problem titled 3 consecutive odds, or we'll explore the logic to determine if a sequence of 3 consecutive odd numbers exists within an array. Let's dive in and break this down step by step. The problem is called 3 consecutive odds. In this problem, you are given an integer array called ARR, and your task is to determine whether there are 3 consecutive odd numbers within the array. If such a sequence exists, you return true, otherwise, you return false. Now, let's break down the input and output format. The input is an integer array ARR with a length of n, where each element, i, is an integer within the range of 0 to n1. The output is simply a Boolean value, true if there is at least one sequence of 3 consecutive odd numbers, and false if there is not. To understand this better, let's look at some examples. In the first example, the input array is 2, 6, 4, 1. The output is false because the array does not contain 3 consecutive odd numbers. The only odd number in the array is 1, and it is not part of a sequence of 3 consecutive odd numbers. Now, in the second example, the input array is 1, 3, 5, 7, 9. The output here is true because the sequence 1, 3, 5 contains 3 consecutive odd numbers. In fact, there are additional sequences such as 3, 5, 7, and 5, 7, 9 that also qualify. However, as soon as we identify one such sequence, we can conclude and return true. Finally, in the third example, the array 2, 4, 6, 8, 10 is given. For this input, the output is false because the array contains no odd numbers at all. Without any odd numbers, it is impossible for the array to have 3 consecutive odd numbers. Now, let's consider some constraints and edge cases. The length of the array will always be between 1 and 1000, and the values in the array can be as large as 10⁻⁹. For edge cases, if the array length is less than 3, like 1, 3, it's impossible to have 3 consecutive numbers, so the result should be false. If the array consists entirely of even numbers, it should also return false. Conversely, if the array contains only odd numbers and its length is at least 3, the result will always be true. For mixed arrays of odd and even numbers, the function must identify if any 3 consecutive numbers are odd. Lastly, since the values in the array can be very large, the solution must be efficient to handle these cases. To solve the problem of finding 3 consecutive odd numbers in an array, we can start by considering a straightforward brute force approach. The intuition here is simple. For every index in the array, check the current element and the next 2 elements to determine if all 3 are odd. Specifically, we iterate through the array from the first index up to n3 to ensure we don't go out of bounds. At each step, we check if the current element, the next one, and the one after that are all odd using the condition ARR j %2 equals 0. If we find a group that satisfies this condition, we immediately return true. Otherwise, after finishing the loop, we return false. While this approach is straightforward and efficient in terms of time complexity running in O(n), since we process each element exactly once, it may perform unnecessary checks even when the answer is already clear early on. This leaves room for optimization, as we'll see shortly. Now, to optimize the solution, we can use a sliding window approach that eliminates redundant calculations. Instead of checking 3 separate elements for each index, we can maintain a running count of consecutive odd numbers. Here's how it works. As we traverse the array, we check whether each element is odd. If it is, we increment a counter that keeps track of consecutive odd numbers. If we encounter an even number, we reset the counter to 0 since the streak is broken. If at any point the counter reaches 3, we know we've found 3 consecutive odd numbers, so we immediately return true. If the loop completes and no such sequence is found, we return false. This approach is not only intuitive but also efficient, as it avoids redundant checks and ensures we terminate the loop as soon as we find the solution. The time complexity remains O(n), but the early termination makes it faster in practice. The space complexity is still O(1), as we only use a single counter variable. When comparing the brute force and sliding window approaches, both share the same O(n) time complexity on paper, but the sliding window method is more efficient in real-world scenarios. This is because it avoids redundant checks by terminating as soon as a valid group of 3 consecutive odd numbers is found, whereas the brute force approach continues iterating through the array even after the result is clear. Additionally, the sliding window approach is just as simple to implement and doesn't add complexity to the code. While alternative methods using data structures like queues could also solve this problem, they would increase the space complexity unnecessarily. For example, maintaining a queue of 3 elements would require extra memory, which isn't needed with the counter-based sliding window solution. Overall, the sliding window approach strikes the best balance between simplicity, efficiency, and resource usage, making it the most practical choice for this problem. The problem asks us to determine if there exists a group of 3 consecutive odd numbers in a given array. If such a group is found, we return true. Otherwise, we return false. To solve this, we start by validating the input. If the array has fewer than 3 elements, it's impossible to form a group of 3 consecutive numbers, so we return false immediately. Next, we iterate over the array using a loop. The loop runs from index 0 to len, 3, which ensures that we can safely access 3 consecutive elements without running into out-of-bound errors. This setup allows us to systematically check every possible group of 3 numbers in the array. For each index in the loop, we check whether all 3 numbers in the current group are odd. This involves verifying 3 conditions. The first number, I, must be odd, the second number, I plus 1, must also be odd, and finally, the third number, I plus 2, must be odd as well. If all 3 conditions are satisfied, we immediately return true. This early exit is an optimization that prevents unnecessary checks once we know the condition is met. If the loop completes without finding any group of 3 odd numbers, we return false by default. This ensures that the function handles all cases where no valid group exists. This algorithm is built on a few key insights. First, even though we don't explicitly maintain a sliding window, the process of checking 3 consecutive elements at each step mirrors the concept of sliding a window of size 3 across the array. Second, the early exit optimization significantly improves performance in cases where a valid group is found early in the array. The algorithm's efficiency is evident in its time complexity of O(n), as we only traverse the array once. Additionally, the space complexity remains O(1), because we don't use any extra data structures. Lastly, it handles edge cases such as arrays with fewer than 3 elements, arrays with no odd numbers, and arrays where odd numbers aren't grouped consecutively. If multiple valid groups exist, we simply return true as soon as the first group is found. The algorithm processes the input array directly, ensuring minimal space usage. A single loop index I is used for iteration, and no additional data structures or memory allocations are required. To see this in action, let's consider an example with the input 1, 3, 5, 7, 2, 6. We start with the first index, I equals 0, and check the group of 3 numbers, 0 equals 1, 1 equals 3, and 2 equals 5. Since all 3 numbers are odd, we immediately return true. This demonstrates how the algorithm quickly identifies a valid group without further unnecessary checks. Now, let's look at a different example with the input 2, 4, 6, 8, 10. We begin with I equals 0 and check the first group of 3 numbers, 0 equals 2, 1 equals 4, and 2 equals 6. None of these numbers are odd, so we move to the next index. For each subsequent group, the same pattern continues, and no group of 3 odd numbers is found. After completing the loop, we return false, as the condition is not satisfied for any group in the array. This example highlights how the algorithm correctly handles cases where no valid group exists. The time complexity of the algorithm is O(n), where n is the length of the array, because we perform a single traversal with constant time checks at each step. The space complexity is O(1), as we don't use any additional data structures apart from the input array and a few variables. The algorithm is already optimal for the problem's constraints, as it minimizes both time and space usage. Further optimizations would require modifying the problem's definition or constraints, such as targeting specific patterns of numbers. Overall, this approach balances simplicity and efficiency, making it well suited for this task. The provided solution solves the problem of determining whether there are 3 consecutive odd numbers in the given array. The implementation is concise and efficient, leveraging a linear iteration through the array. First, the method begins by checking if the array has fewer than 3 elements, as it is impossible to find 3 consecutive elements in such a case. If the array length is less than 3, the method immediately returns false. Next, we iterate through the array from the start to the third to last element. This is because we are checking groups of 3 consecutive elements, and attempting to access beyond the array bounds would cause an error. The loop ensures we safely check every possible triplet in the array. Inside the loop, the code checks if the current element, I, the next element, I plus 1, and the element after that, I plus 2, are all odd. This is done using the modulus operator, %2 = 1, which determines whether a number is odd. If all 3 numbers in the triplet are odd, the method immediately returns true, as the condition is satisfied. If the loop completes without finding any such triplet, the method concludes that no 3 consecutive odd numbers exist in the array and returns false. The algorithm runs in O(n) time, where n is the length of the array, as it involves a single pass through the array. The space complexity is O(1), as no additional data structures are used. This makes the solution efficient and well suited for the problem constraints. This is the Java implementation of LeetCode problem number 1550, 3 consecutive odds. The logic mirrors the provided Python solution, iterating through the array to check for 3 consecutive odd numbers. Key differences include the use of Java's type declarations and array indexing syntax. The method loops through the array, and if a triplet of odd numbers is found, it immediately returns true. Otherwise, it returns false at the end of the iteration. In this problem, we are tasked with determining if an array contains 3 consecutive odd numbers. If such a triplet exists, we return true, otherwise, we return false. Let's start with the first example where the input array is 2, 6, 4, 1. First, we check the length of the array, which is 4, this is greater than 3, so we can proceed with our iteration. On the first iteration, when I equals 0, we check if the first element, 2, is odd using ARR, 0, %2 = 1. Since 2 is even, we move to the next index. On the second iteration, when I equals 1, we check if 6 is odd. Again, it is even, so we continue. On the third iteration, I equals 2, the value 4 is checked and is also even. At this point, we cannot form a triplet starting at index 2 because we've reached the end of the array. Therefore, no triplet of consecutive odds exists in this example, and we return false. Now, let's consider the second example with the input array 1, 3, 5, 7. The length of the array is 4, so we proceed with the iteration. On the first iteration, when I equals 0, we check if 1 is odd, and it is. Next, we check if 3 is odd, and it is as well. Then, we check the third element, 5, which is also odd. This means we have found a triplet of consecutive odd numbers, 1, 3, 5. Since the condition is met, we immediately return true. Let's move on to the next example, where the input is 1, 2, 3, 5, 7. The length of the array is 5, so we can proceed. On the first iteration, when I equals 0, we check if 1 is odd, and it is. However, the next element, 2, is even, so we move to the next index. On the second iteration, when I equals 1, we check if 2 is odd, and since it is even, we continue. On the third iteration, when I equals 2, we check if 3 is odd, and it is. Then, we check if 5 is odd, which it is, and finally, we check if 7 is odd, which is also true. This confirms that a triplet of consecutive odd numbers, 3, 5, 7, is found, and we return true. To summarize, the algorithm works by iterating through the array and checking every triplet of consecutive elements. A triplet satisfies the condition if all 3 numbers are odd, which is determined using the condition number %2 = 1. The loop terminates as soon as a valid triplet is found, allowing us to return early. If no triplet is found by the end of the iteration, the function returns false. In terms of complexity, the time complexity is O(n), where n is the length of the array, as we only traverse the array once. The space complexity is O(1), because no additional data structures are used. This makes the algorithm efficient and straightforward. Here, we analyze the time complexity of the algorithm. The first step is input validation, where we check if the length of the array is less than 3. This operation is constant time, or O(1), because it simply evaluates the length of the array. Next, we have the iteration, which is handled by a for loop running from the first index to the third to last index, resulting in a total of n2 iterations. During each iteration, we perform 3 modulo operations and 3 comparisons, all of which are constant time operations. This means the total work done in each iteration is O(1), and when multiplied by the number of iterations, the total time for the loop becomes O(n). Additionally, the function includes an early exit condition, where it stops iterating as soon as 3 consecutive odd numbers are found. While this can reduce the number of iterations in some cases, the worst-case scenario still involves completing all n2 iterations, making the overall loop complexity O(n). Now, looking at the overall time complexity, the best-case scenario occurs when the triplet of consecutive odd numbers is found at the very beginning of the array, leading to an immediate return and a time complexity of O(1). In the worst case, when no such triplet exists in the array, the loop completes all n2 iterations, resulting in a time complexity of O(n). For the average case, we assume that the position of the triplet varies across different inputs, leading to an average time complexity of O(n). Hence, the overall time complexity of the algorithm is O(n). Moving on to space complexity, the input array is passed by reference, meaning no extra space is used for storing it. Additionally, the algorithm only requires a few variables for iteration and comparisons, all of which consume constant memory. Thus, the overall space complexity is O(1), as no additional data structures or dynamic memory are used. Let's compare the current solution to a naive or brute force approach. A naive method would involve generating all possible triplets in the array, each consisting of 3 consecutive elements, and checking if all numbers in each triplet are odd. This approach would generate O(n)(2) triplets, and for each triplet, it would perform 3 modulo operations and comparisons. While this sounds inefficient, the time complexity of the naive approach is still O(n), as the number of triplets is directly proportional to the size of the array. Similarly, the space complexity of the brute force approach remains O(1), as no additional storage is required. The current solution, on the other hand, optimizes the process by minimizing redundant checks and avoiding unnecessary computations. Despite these optimizations, the time complexity remains O(n), and the space complexity stays O(1), matching the naive approach in terms of theoretical bounds. The key takeaway is that the current solution is already optimal, achieving linear time complexity and constant space complexity, while efficiently handling both best and worst-case scenarios. When solving this problem, there are several common mistakes to watch out for. First, ignoring edge cases can lead to errors. For example, if you don't account for arrays with fewer than 3 elements or arrays with all even numbers, you might make incorrect assumptions or encounter runtime errors. Always handle special cases like empty arrays, arrays with only 1 or 2 elements, or arrays that contain no odd numbers at all. Another common pitfall is implementing the sliding window approach incorrectly. For instance, if you forget to remove the contribution of the leftmost element when moving the window forward, you'll end up with overlapping computations, which can produce incorrect results. Finally, relying on brute force solutions, such as using nested loops to check all subarrays of size 3, can be inefficient. This increases the time complexity to O(n²), which is unnecessary when a more efficient O(n) solution using the sliding window technique is available. Another area where mistakes often occur is in the odd number check. For example, some people use the condition if number %2 equals 1 to check if a number is odd. While this may work for positive numbers, it fails for negative odd numbers because -3%2 equals -1. Instead, use if number %2 is not equal to 0 to ensure the check works for both positive and negative numbers. Additionally, it's important to fully understand the problem requirements. A common misunderstanding is to check for groups of 3 odd numbers anywhere in the array, rather than consecutive odd numbers. This misinterpretation can lead to solving an entirely different problem. Now, from an interview perspective, this problem is an excellent opportunity to demonstrate the sliding window technique. Be prepared to explain how this approach minimizes redundant calculations and improves efficiency. Discussing edge cases during the interview, such as arrays with fewer than 3 elements or arrays containing only even numbers, will show thoroughness in your solution. It's also vital to highlight your awareness of time complexity. Explaining how sliding window reduces the complexity from O(n² to O(n) will demonstrate your ability to optimize solutions. Finally, Communicate your thought process clearly, especially when transitioning from a brute force approach to the more efficient sliding window technique. This problem also shares similarities with other problems on LeetCode that you might find helpful for practice. For instance, LeetCode 1004, max consecutive ones 3, or LeetCode 485, max consecutive ones, both focus on finding streaks of specific values in an array. Similarly, LeetCode 209, minimum size subarray sum, and LeetCode 3, longest substring without repeating characters, challenge you to efficiently track subarray or substring conditions. Exploring these problems can deepen your understanding of sliding window and related patterns. Now, when it comes to alternative approaches, brute force is the simplest to implement, but it's highly inefficient for large arrays due to its n² complexity. This approach may be suitable for small input sizes or when you're initially prototyping a solution. On the other hand, the sliding window approach is much more efficient, offering n complexity. However, it does require careful implementation to ensure the window boundaries are managed correctly, which can add a layer of complexity to debugging. Sliding window is generally the best choice for large input sizes, making it a key technique to master. Finally, let's talk about the two-pointer approach. While it's similar in concept to the sliding window, it's slightly different in how the pointers are managed. For this particular problem, the two-pointer approach can be harder to implement because it requires more careful tracking of conditions within the window. However, it becomes a valuable tool when you need to incorporate additional constraints or conditions into your solution. Understanding when to apply this technique is just as important as knowing how to implement it. By mastering both sliding window and two-pointer techniques, you'll be well prepared to tackle a wide range of problems efficiently and confidently. Great work! In this session, we reviewed the problem 3 consecutive odds, summarized our approach, and highlighted key takeaways. Remember to practice consistently and refine your problem-solving strategies. Thanks for joining, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!